Chimney caps and spark arresters play an essential role in protecting the flue system from moisture, wildlife, and embers, but they must meet specific listing and performance requirements to be considered safe and code compliant. One fundamental rule is that the net free area of the cap or spark arrestor must be at least 4 times greater than the cross-sectional area of the flue it serves. This ensures that the addition of the cap does not restrict draft or create excessive resistance that could impair the chimney's performance. Spark arresters must be designed so that they do not allow the passage of spheres measuring 1/2 inch in diameter, while also ensuring they do not block the passage of spheres measuring 3/8 of an inch. This standard mesh size, typically a 3/4 inch expanded metal pattern that produces 3/8 inch openings, is required to prevent the escape of burning embers without impeding the flow of exhaust gases. In addition, chimney caps are required to be removable at the top to allow for proper inspection and cleaning of the flue, as a permanently affixed cap would interfere with maintenance and cleaning procedures. NFPA 211 also provides specific guidance for multi-flue chimney caps. According to Section 4.62, the minimum vertical distance from the underside of an unlisted multi-flue chimney cap to the top of the flue it covers must be equal to the lesser dimension of the flue's opening. For example, if a multi-flue cap is covering 2 flues that each measure 13 by 13 inches, the lesser dimension is 13 inches, meaning the underside of the chimney cap must be positioned at least 13 inches above the top of the highest flue. This requirement ensures that the cap provides adequate clearance to maintain proper draft while preventing turbulence, smoke spillage, or heat buildup that could damage the cap or the chimney structure. Collectively, these requirements ensure that chimney caps and spark arresters function safely, maintain proper draft, and comply with national standards for performance and fire protection. Flue tiles are required to extend above the chimney crown, but their height is carefully limited to ensure proper function, durability, and safety. The standard requirement is that the flue liner must project at least 2 inches above the crown, but no more than 4 inches above it. These dimensions are not arbitrary. They serve important performance purposes. Extending the flue tile at least 2 inches above the crown prevents water from draining across the crown surface and directly into the flue. Without that projection, water could be funneled straight into the chimney, increasing moisture damage, accelerating liner deterioration, and contributing to rust, decay, and other internal problems. This 2-inch minimum also provides enough vertical surface for a standard chimney cap to be properly attached. Most caps require a certain amount of exposed liner to allow secure bolting or banding, and this minimum projection ensures that a cap can be safely and reliably installed. At the same time, the flue tile should not extend more than 4 inches above the crown. When too much liner is left exposed, the surrounding cold air cools the flue gases rapidly as they enter the exposed section of tile. This cooling slows draft, encourages condensation, and leads to the formation of creosote. Over time, excessive creosote accumulation increases fire risk and reduces system efficiency. Additionally, a tall, exposed section of flue tile creates structural challenges. For multi-flue chimneys in particular, flue tiles that extend too high require unusually tall chimney caps to provide adequate clearance. These oversized caps can become unstable in high winds and place stress on the crown or mounting points, increasing the likelihood of damage. By maintaining the flue tile extension between 2 and 4 inches, the chimney system protects against water intrusion, allows for proper cap installation, maintains stable draft temperatures, and avoids the instability associated with oversized multi-flue caps. This simple requirement plays an important role in the overall safety and longevity of the chimney. An ASTM C1283 masonry chimney crown is a critical structural and weather protective component designed specifically to maintain and preserve the top of the chimney. This standard outlines several construction requirements that ensure the crown sheds water effectively, resists cracking, and accommodates the thermal movement of the flue. Each specification serves a distinct purpose in the long-term durability and safety of the chimney system. The crown must project a 2-inch overhang beyond the outside wall of the chimney. This projection is essential because it deflects rainwater away from the brick or block below, preventing water from cascading down the vertical masonry surfaces. Without this overhang, the face of the chimney becomes a collection point for runoff, accelerating saturation, freeze-thaw damage, efflorescence, and mortar erosion. Complementing the overhang is the requirement for a drip slot on the underside, positioned at least 1.5 inches away from the chimney wall. The drip slot creates a physical break in surface tension, ensuring that water detaches and falls to the roof rather than tracking inward and running down the masonry. Together, the overhang and drip slot work as the chimney's first line of defense against moisture intrusion. The crown must also have a minimum 2-inch thickness at the outside edge and must be reinforced with 1/2-inch wire mesh. The thickness provides structural strength and resistance to weathering, while the reinforcing mesh greatly reduces the likelihood of cracking due to temperature changes, settlement, or shrinkage. Chimney crowns are exposed to harsh conditions, sun, wind, rain, snow, and rapid temperature swings. Reinforcement distributes stress throughout the crown, preventing the hairline cracks that otherwise develop, widen over time, and eventually lead to water infiltration. Another requirement is that the crown be constructed with a slope of at least 10 degrees, descending from the flue toward the edges. This slope is crucial because it directs water away from the flue liner and off the chimney entirely. A flat or shallow sloped crown allows water to pond, freeze, and seep into cracks, accelerating deterioration. The 10-degree slope ensures proper drainage even in heavy or wind-driven rain. Proper thermal movement is also addressed through the requirement for a bond break between the crown and the flue liner. Flue tiles expand significantly when heated, while the crown does not expand at the same rate. If the crown is bonded directly to the flue, thermal expansion can cause the crown to crack or lift. A bond break, typically achieved using a compressible material, lets the flue move freely without transferring stress into the crown. This is also why the flue must extend 2 to 4 inches above the crown, striking the balance between water protection, cap installation requirements, and limiting the amount of exposed tile that could cool flue gases excessively. For non-masonry systems, metal chimney crowns are required to lap a minimum of 4 inches down the sides of the chimney and must include a flared drip edge. This extended lap protects the vertical surfaces from water intrusion at the crown to masonry interface, while the drip edge ensures water detaches cleanly rather than running down the structure. Taken together, these ASTM C1283 requirements create a chimney crown that protects the entire upper structure from water, thermal stress, and mechanical deterioration. Each detail, overhang, drip slot, reinforcement, slope, bond break, and proper flue projection works together to ensure the crown performs its essential job of keeping the chimney dry, stable, and long-lasting. One of the most common and destructive problems found in the chimney industry is the chimney crown being bonded directly to the flue tile. This seemingly simple construction mistake violates basic engineering principles and leads to predictable failure. A clay flue liner undergoes significant thermal expansion every time a fireplace or wood-burning appliance is used. Vitrified clay tile has a coefficient of thermal expansion of approximately 4 to 5 multiplied 10 superscript minus in slash degree F, which means that as the flue heats up, the liner measurably increases in length. Because the flue liner is supported at the top of the smoke chamber at its base, the lower end is effectively fixed in place. When heated, the liner cannot expand downward, so the only possible direction of expansion is upward. If the chimney crown has been bonded directly to the flue tile without a proper bond break, the flue cannot move freely. Engineering principles dictate that when thermal expansion is restrained, force must be released somewhere in the system. The result is a series of failure mechanisms, all of which are commonly observed in the field. In some cases, the joints between the flue tiles absorb the stress and are crushed or compressed. In other situations, the liner attempts to expand upward but is restrained by the crown, causing the crown to crack. Sometimes the entire chimney crown and the flue tile lift upward as one unit, creating horizontal cracks in the brick course directly below the crown. The liner itself may also chip, spall, or deteriorate because vitrified clay has a very high modulus of elasticity, making it extremely stiff. When stiff materials are forced into movement but prevented from expanding, they transfer those stresses into the softer surrounding materials. This is why the crown, mortar joints, and masonry, being comparatively weaker, tend to fail first. The most common failure pattern seen in the field is the top flue tile thermally expanding through the crown. During heating, it forces its way upward, cracking the bonded crown. Once the liner cools, it shrinks back to its original length. However, because the crack in the crown creates frictional restraint, the top tile often does not fully return to its original position. Over time, this leaves a visible separation gap between the top flue tile and the second flue tile below it. Inspectors frequently find this telltale vertical gap, which is a clear indicator of thermal expansion stress and bond failure. Another serious consequence involves buckling. When both the bottom and top of the flue liner are restrained, bottom fixed by the smoke chamber, top fixed by the crown, the liner behaves like a column under compressive load. As the internal stresses build, the liner may not fully expand upward, so it begins to deflect sideways. This buckling effect may be extremely small, sometimes only a millimeter of lateral movement per heating cycle, but over years of operation, these millimeters accumulate into centimeters. The result is offset flue tiles, a dangerous condition that compromises draft, weakens the structural alignment of the liner, and increases the risk of heat transfer to surrounding combustibles. In short, bonding a chimney crown directly to the flue tile sets off a chain reaction of structural failures. Thermal expansion is a predictable and unavoidable behavior of vitrified clay tiles. If the flue cannot expand freely, the system will relieve that stress through cracking, lifting, crushing, deterioration, or long-term buckling. This is why STMC 1283 and NFP 211 require a bond break between the crown and the flue tile. Without this allowance for movement, failure of the crown or the liner is not merely possible, it is inevitable. Proper chimney liner construction is essential for both safety and performance, and several standards guide how flue liners must be installed within a masonry chimney. The best chimney liner systems run vertically in a straight line because straight vertical flues draft more efficiently and reduce turbulence and soot accumulation. When a change in direction is unavoidable, the bend must be made with a clean saw-cut liner section, and the angle of deviation from vertical may not exceed 30 degrees. This ensures that the flow of exhaust gases remains smooth and that creosote formation is minimized. The joints between clay flue tiles must be constructed with a refractory mortar specifically designed for high temperatures. These joints should measure between 1/16 inch and 1/8 inch in thickness and must be struck flush on the inside of the flue. Flush internal joints prevent soot and creosote from accumulating in mortar ledges and reduce the risk of chimney fires. The chimney walls that surround the liner must be made of at least 4 inches of nominal masonry on all sides to maintain structural integrity and provide proper heat dissipation. One of the most important requirements is that the liner must not be bonded to the surrounding chimney structure. Clay flue tiles expand when heated, and the chimney walls do not expand at the same rate. For this reason, the liner must be free to move independently with thermal expansion. The separation space should be no more than the thickness of the liner wall, typically 5/8 inch for standard flue tiles. Excessive spacing creates structural weakness, while a bonded liner creates stress that inevitably leads to cracking, crushing of mortar joints, or buckling of the flue during thermal cycles. There's long-standing confusion in the building industry regarding the amount of space required around a flue liner. NFP 211 references a clearance range of 1/2 inch to 4 inches between the liner and the chimney wall, which has left many builders uncertain about the correct dimension. The reason for this variation is not actually about draft or safety. It stems from differences in seismic requirements. In seismic zones, chimneys must resist lateral movement during earthquakes. To accomplish this, reinforcing steel rebar is embedded in the chimney structure and must be fully surrounded by concrete or grout. In these areas, the space between the liner and the chimney wall is often grouted solid to lock the reinforcement in place. However, because solid grouting would bond the liner to the chimney and prevent thermal expansion, ASTM-C 1283 directly addresses this issue. The standard requires that when seismic reinforcing makes it necessary to grout the space solid, the flue liner must be wrapped in ceramic fiber paper capable of withstanding temperatures of at least 2,100 degrees Fahrenheit. This wrapping prevents the grout from bonding to the tile while still allowing the liner to expand freely. In our opinion, and increasingly in modern best practice, all flue liners should be wrapped with ceramic fiber insulation, even in non-seismic regions. The wrap not only prevents bonding, but also provides insulation value. Insulated liners maintain higher internal temperatures, which improves drafting and reduces creosote formation. We will explore these thermal advantages in later sections. ASTM-C 1283 also specifies important safety clearances. Combustible materials must be kept at least 2 inches away from the exterior chimney wall, unless the chimney contains at least 12 inches of solid masonry between the inner face of the liner and the combustible material. This rule protects surrounding structures from excessive heat transfer and reflects the principle that thicker, solid masonry provides superior fire protection. Together, these construction requirements, vertical alignment, proper joint dimensions, sufficient wall thickness, freedom of thermal movement, appropriate separation, and compliance with seismic and combustible clearance standards, form the foundation of a safe, durable, and efficient chimney system. Chimney crickets and proper flashing are essential components in preventing water infiltration around a masonry chimney. Because chimneys interrupt the roof plane, they create natural water collection points that must be controlled through correct construction practices. Step flashing and counter flashing work together to seal the roof to chimney intersection, while the chimney cricket diverts water away from the uphill side of wider chimneys. Building codes require a 2-inch clearance to combustible materials around the exterior of the chimney where it passes through the roof. This clearance protects the structure from the elevated temperatures that can radiate through the chimney walls. When roofing is installed, this 2-inch gap must not be filled with combustible material. A common and acceptable method to bridge this gap structurally is to fasten strips of sheet metal over the opening. These metal strips cover the clearance space and extend onto the roof sheathing by an additional 4 inches. They can be secured with construction adhesives such as liquid nails. Once the roofing underlayment, step flashing, and counter flashing are installed over top, this assembly reinforces the metal-covered gap and restores structural stability while maintaining the required non-combustible clearance. Step flashing is installed where the roof surface meets the side of the chimney. Each piece of step flashing is woven into the roof shingles so that water flowing down the roof is continuously redirected outward and away from the chimney. However, step flashing alone is not sufficient without properly installed counter flashing. Counter flashing is embedded into the chimney itself. The top edge must be regletted into a mortar joint, a groove cut into the brickwork, so the flashing is locked into the chimney rather than simply surface mounted. After the reglet is sealed, the bottom edge of the counter flashing overlaps the step flashing, forming a shingled, watertight assembly that accommodates normal masonry expansion and contraction. For chimneys 30 inches wide or greater, a chimney cricket is required on the uphill high side. Wider chimneys act as water dams, causing rainwater and snowmelt to accumulate behind them. A properly built cricket splits and diverts this water around the chimney. The height of the cricket is determined by the roof pitch, but its ridge is typically horizontal to efficiently channel water to either side. Together, the 2-inch clearance to combustibles, sheet metal bridging, woven step flashing, regletted counter flashing, and properly constructed chimney cricket create a comprehensive, long-lasting water and heat management system. When these components are installed correctly, the chimney remains protected from water intrusion, the roof structure remains shielded from excessive heat, and the entire assembly performs reliably for decades. The construction of a masonry chimney begins with the basic requirement that the chimney walls be at least 4 inches thick, as specified by building code. While this minimum thickness is technically permitted, we strongly recommend constructing chimneys with 8-inch thick walls. An 8-inch masonry wall provides far greater rigidity, especially in high-wind environments where tall chimneys are vulnerable to lateral loading. Thicker walls also offer improved protection against heat transfer, keeping combustible structural members safely outside the required clearance zones. In addition, the increased mass of an 8-inch wall provides a higher factor of safety when correcting for construction imperfections, such as uneven joints, misaligned flue liners, or minor deficiencies in workmanship.